2.3 Spectrum spreading communication. The theory of spectrum spreading has existed since the 1960s, however, creating a spreading signal to expand the signal into a bandwidth much wider than the transmission band was a major challenge. Spreading signals must be rectangular waves with extremely short durations, and it was difficult to generate such high-speed signals using processors composed of vacuum tubes or early transistors. It was not until the mid to late 1980s, when infrastructure technology had matured, that attempts at spectrum spreading communication began in earnest, centered around Qualcomm in the US, under the name CDMA. At the time, the TIA responsible for North American standardization formed the TR-45 committee to review next-generation cellular technologies based on CDMA. CDMA was already a proven technology, having been applied to the European GSM network. On May 5, 1992, the TIA established a new subcommittee, TR-45.5, to set standards for digital cellular frequency spreading, despite it being unproven. Concurrently, the Korean government decided on Qualcomm's CDMA for its next-generation digital cellular system, and, in 1997, became the first in the world to commercialize a CDMA digital cellular network. The commercialization of CDMA led Korea to become a powerhouse in mobile communication technology and drew global interest. Currently, technical standards for IMD-2000 are progressing actively, and Europe is also pursuing spectrum spreading as the multiple access method for next-generation mobile communications. This suggests that CDMA is considered highly efficient for cellular systems and the most suitable technology for next-generation mobile communication. To differentiate from Qualcomm's CDMA, the European version proposes using independent spreading codes for base station signals, referred to as asynchronous CDMA. While the Qualcomm method used in Korea applies the same generator polynomial and distinguishes codes only by their time offsets, European CDMA uses codes generated from entirely different generator polynomials. 2.3 Spectrum spreading. Spectrum spreading communication, or simply spread spectrum, is largely divided into two types, DSSS and FHSS. Frequency hopping was primarily used for secure communications between military aircraft, or between aircraft and the ground. The PCS we use today employs DSSS, a different spreading method. Spread spectrum is a method of transmitting a signal over a bandwidth much larger than the bandwidth of the information signal. To spread information data, it must be multiplied by a modulation bit rate much faster than the information bits. Multiplying by a much faster modulation bit means transmitting the information over a wider area than the original bandwidth. However, there is another technology called multiplexing that also transmits over a wider band. Multiplexing bundles the information of many people into a signal with a much wider bandwidth. Since it combines many users' transmission bands, the total bandwidth naturally becomes wider. From an individual's perspective, since their data is transmitted over a much wider bandwidth, it might seem identical to spread spectrum. However, the difference is that multiplexing transmits multiple users' signals bundled together in that wide band, whereas spread spectrum expands a single user's signal to fill that band. You can think of it as the difference between many people riding a bus versus one person riding that entire bus alone. 2.3 To frequency hopping and direct sequence. Frequency hopping and direct sequence are distinguished by which component of the information signal amplitude, frequency, or phase is modulated by the spreading code. Modulation, the core technology of electrical communication, involves converting the source information into changes in an electrical signal and restoring those changes at the receiver. This is typically done by reflecting information in the amplitude frequency, or phase of the transmission signal. Generally, the spreading signal is much faster and occupies a much wider bandwidth than the information signal. To spread information, the spreading signal must be modulated onto the information signal. Methods that reflect the spreading signal in frequency or phase, similar to FM, are classified as frequency hopping. On the other hand, reflecting the spreading signal in the amplitude of the information signal can be achieved by multiplying the modulation signal and the modulated signal. Spread spectrum technology can be described as performing spread modulation one more time on a signal that has already been modulated. More specifically, baseband modulation and spread modulation are performed sequentially. The signal after spread modulation is shown in Figure 2.10. In Figure 2.10, S is a time function of the spreading code. The PN code is widely used as a spreading code, and in European CDMA, gold codes made by combining to PN codes are used. The signal in Figure 2.10 represents the spreading of a PSK signal, where the information P is reflected in the phase of the carrier. To spread the spreading signal S is modulated once more onto the signal already modulated by the carrier specifically, by reflecting the spreading signal in the amplitude variations of the modulated signal. 2.3 Quantitative analysis of spread spectrum communication. The information signal that has undergone direct sequence spreading is expressed as the product of the information signal, the spreading signal, and a carrier wave with a center frequency of omega c. In equation 2.14, the signal for spread modulation is G, and D is the data signal to be transmitted, represented as PS cos, where PS denotes the magnitude of D generally. The bit rate of G, denoted as FC, is significantly higher than the bit rate of D, denoted as FB. Because the spreading signal rate is so much faster compared to the information bit rate, the units of the spreading signal are specifically referred to as chips. Accordingly, the transmission speed off these chips is called the chip rate. Since a very fast signal in the time domain occupies a very wide band in the frequency domain, multiplying the information signal by the spreading signal results in the signal V appearing as very short duration data, as shown in Figure 2.11. In other words, regardless of the original information data, once spread modulation occurs, the bit rate of the modulated signal is converted to the chip rate of the spreading signal used for the process. When spreading occurs, it manifests as an increased bit rate in the time domain, while in the frequency domain, the transmission band expands. That is, the expansion of the transmission bandwidth has been achieved. Figure 2.12 illustrates how a modulated signal is received through a channel, and then demodulated at the receiver by multiplying it by the same modulation signal to recover the original data. Modulating or demodulating an information signal into an RF signal involves multiplying it by a carrier wave. The same principle applies to spread modulation. You multiply the signal to be modulated by the spreading signal. This process functions much like a toggle switch. Multiplying the signal by the modulation signal once performs modulation, and multiplying the resulting signal by that same modulation signal a second time performs demodulation or, in this context, despreading. The information signal is spread modulated by being multiplied by the spreading signal G, which then passes through the channel to be received by the receiver. To recover the information signal from this spread state, the receiver multiplies it by G once again. Of course, since the carrier wave is also multiplied during this process, the information signal can be demodulated from the carrier. It is important to note here that, as modulation is essentially a multiplication operation, the specific order whether you perform spread modulation and demodulation first, or carrier modulation and demodulation first does not carry significant mathematical or engineering weight. In a linear system, the commutative property of multiplication allows these processes to be interchangeable in theory. Let's consider what the spread signal undergoes as it passes through the channel. As shown in Figure 2.13, we can imagine the presence of jamming, which is a form of intentional noise on the transmission path. The jamming signal, J, acts as an interference to the signal we wish to transmit and receive, thus, it can be understood as encompassing all signals other than the desired one. The jamming signal affects the entire spread bandwidth with its magnitude, Pj. This type of jamming signal influences the amplitude, phase, and frequency of the transmitted information signal. The received signal entering the receiver is expressed as the sum of the information signal and the jamming signal, as shown in equation 2.15. At the input stage of the receiver, to demodulate the spread component, the receiver generates a signal G identical to the spreading signal used in the transmitter via a local oscillator and multiplies it with the received signal. Subsequently, the RF carrier component will also be removed through low-pass filtering, which occurs alongside the demodulation process. Here, implementing the mathematical expression of multiplication refers to coherent detection, where demodulation is performed while the phase and frequency information are known. Once this demodulation process is complete, the signal is recovered and then subjected to low-pass filtering. The signal output from the integrator, which acts as the low-pass filter, is as shown in equation 2.16. When the signal from equation 2.15 passes through a low-pass filter, all high-frequency components, specifically the omega CT terms, are eliminated. In other words, high-frequency carrier components such as cos or sin are completely filtered out. Reflecting this, equation 2.15 is simplified into equation 2.16. In equation 2.16, it can be observed that the information signal and the jamming signal are completely separated. Consequently, by despreading the received signal at the demodulator, the information signal can be effectively protected from interference that entered during transmission. This is the fundamental reason for using spread modulation for information signals. 2.3 for spread fader, which is processing gain. We will now examine what elements of the spectrum spreading effect protect the information signal from jamming, and to what degree this protection is provided. To achieve this, we must identify what determines the effective power of the jamming signal, which serves as a metric for how much an interference signal can actually affect the information signal. Understanding the factors that govern this effective power is crucial, as it reveals how the spread spectrum system inherently suppresses unwanted interference while restoring the desired data. First, by calculating the power spectral density of the interference component, which is the right-hand term of equation 2.16, and deriving the corresponding probability density function for potential errors, we obtain equation 2.17. In this context, theta represents the phase difference between the carrier wave transmitting the information signal and the jamming signal. For the jamming signal to exert its maximum influence on the carrier signal, cos theta must equal 1, which occurs when there is no phase difference between the two signals. Conversely, the jamming signal has zero impact when there is a phase difference of 90 circ. We define the jamming power generated when the phase difference is 45 circ as the effective jamming power, which is defined as follows. The effective jamming power, Pj, if shown in equation 2.18, decreases as the ratio of the spreading signal's chip rate to the information signal's bit rate increases. In other words, as the information signal is spread over a wider bandwidth for transmission, the magnitude of the jamming signal that can exert a significant influence on the information signal diminishes. This implies that the more a signal is spread, the more it becomes virtually immune to the effects of jamming. The resistance against jamming can be measured by the degree of spreading. For this reason, we must define an indicator that represents the extent of this spreading, which we call the processing gain. The processing gain is defined as shown in equation 2.19. For reference, Qualcomm, the company that first developed the CDMA cellular system, refers to this as the spreading factor. Because the information signal is spread across an extremely wide bandwidth, its power spectral density is very low. Consequently, it arrives at the receiver appearing to be at, or even below the level of white noise. The receiver's demodulator then processes this wideband, low-power signal. During this process, although both the information signal and the noise were received at low power levels, a critical transformation occurs. The information signal is restored to its original narrowband form with sufficient power, whereas the noise remains spread thin at a low level. In essence, the demodulation process selectively recovers the power of the information signal only. Based on this principle, communication is possible, even at a very low signal-to-noise ratio, provided the transmission bandwidth is wide enough. For reference, in CDMA systems that utilize spread spectrum communication, an acceptable SNR is typically -8 decibels, or lower. This means that in a spread spectrum environment, a situation where the noise is more than 3 times stronger than the signal is actually considered a favorable communication condition. Figure 2.14 illustrates the rough relationship between a given power level and the allocated frequency bandwidth. This essentially comes down to a strategic choice: whether to distribute the energy of the information data evenly across a wide bandwidth, or to concentrate it within a narrow bandwidth. Spread spectrum can be understood as a method that utilizes the entire available bandwidth, while dividing the power across that spectrum. In contrast, conventional narrowband communication can be understood as a method that uses the full available power, but divides the signal by specific frequency ranges.